Organic chemistry. Organic chemistry is a study of organic molecules. Organic molecules are molecules that contain carbon atoms. But now, not all molecules that contains carbon atoms are organic molecules. But all organic molecules will contain carbon atoms. Let's say, for example, we have the following organic molecule. So the organic molecule will have a chain of carbon that is bonded typically to hydrogen atoms. But now, organic molecules are not limited to whereby we have carbon atoms bonded to hydrogen atoms only. We can have an organic molecule whereby we have a chain of carbons and then another carbon being bonded to elements such as oxygen, or we can also look at halogens and different types of elements like that. So now this is also an organic molecule. Remember, we said not all molecules that contains carbon are organic molecules. So if you look at molecules such as carbon dioxide, it contains carbon, but now it is not an organic molecule. So this is considered as an inorganic molecule. So this is not what we're going to focus on this chapter. On this chapter, we're only going to focus on organic molecules. So now, if you look at these two types of organic molecules, we can clearly see now they have different behaviors. For example, in this first one here, we only have single bonds in between carbons and hydrogens. And then if you look at this one, we have now an oxygen bonded to the last carbon. So now these different functionalities of these organic compounds, it is going to now introduce to us different types of categories we can categorize organic molecules. For example, all the organic molecules that have single bonds in between carbons and hydrogens, we call them alkanes. And then now all the organic molecules that have a double bond oxygen on the last carbon, we call them aldehydes. So now, do you see that different organic molecules will fall under different families? So now, these different families, we call them homologous series. So we're going to look at 9 different homologous series, which are alkanes, alkenes, alkynes, haloalkanes, aldehydes, ketones, alcohols, carboxylic acids, and esters. So what is it that makes a homologous series? So all the elements in the same homologous series, of which we refer to in the same family, they must all have the same general formula and the same functional group. So now, when we talk about a general formula, we talk about the relationship between the number of carbons to the number of hydrogens, or the number of any elements we have in that organic compound. And then when we talk about the functional group, we talk about the thing that describes the homologous series. For example, we have seen that alkanes only have single bonds in between carbons and also hydrogen atoms. So these two things here, they are what distinguish between the homologous series. Let's say, for example, we have the following structure of an alkane. We have 3 carbons that are bonded to hydrogen atoms. So you will notice that the general formula of all alkanes will be given as the number of carbons will be equal to 2 times number of carbons plus 2 on the number of hydrogens. So now, if we wanted to determine the chemical formula of this following alkane, we will substitute now the number of carbons in this general equation. Remember now, this general equation is the same for all alkanes. So we're going to substitute now the number of carbons, which is 3. So we're going to put 3. And then if we work out the number of hydrogens, you will substitute now 2 multiplied by 3, and then you add it by 2. So you will see now the number of hydrogens you will get now is 2 times 3, which is 6, plus 2, which is going to be 8. So now for 3 carbons, you will have 8 hydrogens bonded to those 3 carbons. And then this works for all the alkanes. So we said now the functional group is something that actually describes a homologous series. And then we said now in alkanes, the homologous series is described as when we have the carbons bonded to another carbons, and then they are also bonded to hydrogen atoms. So now when you write now the functional group, you don't have to show now the hydrogen atoms. You can just say now we have single bonds in between carbons, and we also have single bond in between carbon and corresponding hydrogen atoms. So now, if you were to describe this functional group in words, you will say now you have a single bond in between carbon and hydrogen atoms, and you also have a single bond in between carbon and carbon. So, but what describes that is what we call now the single bond. So you should just mention that we have those single bonds wherever we see carbon and hydrogen, and also where we see carbon and carbon. So you need to know how to draw the structure of the functional group, and you also need to know how to describe the functional group in words. So now, if you look at this line that we are going to discuss now, we're going to have to understand what is a hydrocarbon. So now, when we talk about a hydrocarbon, we talk about an organic molecule that only consists of carbon and hydrogens. So if we look at alkanes, alkanes only have carbon atoms and hydrogen atoms. So this means an alkane will be a hydrocarbon. Is that okay? So you have to write that in full words, which is now hydrocarbon, but I will just represent it as HC. So alkanes are hydrocarbons because they consist of what? Of carbons and hydrogen atoms only. And then now the second word that we need to understand is the saturation. So now saturation simply means that if ever we have single bonds in between carbons and hydrogens, so we don't have the space to put in another hydrogens, therefore that compound will be saturated. So if we look at alkanes here, we only have single bonds in between carbons and hydrogens, and also in between carbons and carbon. So that means alkanes are saturated molecules. So we'll say now they are saturated because they don't have the space to take whatever hydrogens that we will want to include in that. So that is what describes alkanes. So now, secondly, we need to now move to the second group, which is called alkene. So if we look at alkene, what describes an alkene is that in between the carbons, we are going to have a double bond. So whenever we have a double bond, then we are going to have now an alkene. Remember now, carbon can only bond with what? With 4 bonds. So please make sure now when you draw an alkene or whatever type of structure you draw, you make sure that in one carbon you have 4 bonds. So do you see here we have double bonds, then we're going to have single bonds. So now that means it is 4 here, and then this one will have to have double bonds, single bonds, and then that is 4. So you must make sure that you don't bond a carbon with more than 4 bonds. Okay, so now we say now alkanes is whereby we have a double bond in between what? In between carbons. So if we have a double bond in between the carbons, we are going to have now a different general formula, and then this general formula will describe all the alkenes. So the general formula of alkenes is given as Cn, and then we have H2n. So you will see now for all the number of carbons you have, in this case we have 3 carbons, we are going to always get what? 2 times 3 carbons, which is now going to be 6 hydrogens. And then now if you count the number of hydrogens you have, is going to be 1, 2, 3, 4, 5, 6. It will have to follow this general equation of what? Of alkenes, if ever this element is an alkene. So now we also need to know how to draw the functional group of alkenes. So remember we said now alkenes is when we have double bonds in between carbons. So the minute we have double bonds in between carbons, therefore that will indicate that we have what? We have an alkene. So this is what distinguishes alkenes from other types of groups. It is a double bond in between carbon atoms. So now, for you to describe this in words, you will just say we have what? We have double bond in between carbon. So you can just write it like that. Carbon, carbon, double bond. So that is how you will describe it in words. And that is called a functional group. So now in this functional group or in this homologous series, do you see now we only have carbons and hydrogen atoms. So this means this is a what? This is a hydrocarbon atoms because we have hydrogens and carbon atoms only. So that means it is also a hydrocarbon atom. But now, if we look at this thing here, it is not saturated because now we have a double bond. So now if we have a double bond in between the carbons, therefore this is unsaturated because we can break this bond and then we can fill it with another hydrogens. So now we're going to say this one here, it is not saturated, or we can just say unsaturated. So unsaturated simply means we have double bonds in between the carbons. It's either double or triple bonds. But now remember, if we have single bonds, we say now we have a saturated molecule. Okay, so with that being said, we're going to move on now to the next group, which is called alkenes. So now the way we distinguish between now alkenes, we will see that in between the carbons, we're going to have a triple bonded carbon to carbon, and that is what makes an alkene. So remember, one carbon must bond with what? With 4 bonds. So in this case, we have bonded 3, so that means it must bond with 1 hydrogen. And then if you look at this carbon, it has already been bonded with 4 bonds. So that means now it cannot be bonded with any hydrogen. So now it will only be this one that is left to be bonded with these 3 hydrogens. Okay, so remember now the general formula of what? Of alkanes, we have to also subtract 2 hydrogens. So now from the general formula of alkenes, which is now H2n, we're going to subtract 2 number of hydrogens. And this general formula should give us the molecular formula for all alkenes. So now, if you look at this, we can substitute the number of what? The number of carbons we have. In this case, we have 3 carbons. So we're going to substitute 3 And then if we substitute 3, do you see now if we say 2 multiplied by 3, we are going to have 6. And then if we say 6 minus 2, then we're going to get how much? We're going to get 4 hydrogens. So if you look at this structure here, for 3 carbons, we have now 1, 2, 3, 4 hydrogens. Therefore, we can clearly see now the general formula actually describes this group which is called alkenes. Okay, so now for alkenes, if you look at alkenes, the functional group will be, we have triple bonds in between carbons. Okay, and then if we have triple bonds, obviously we're going to have single bonds that will be bonded to other carbons, or maybe, for example, bonded to a hydrogen. But now what makes an alkene to be an alkene is this triple bond that we see in between two carbons. So if we were to describe that in ways, we're going to say what? We have now the triple bonds in between carbon atoms. That is how you can describe it in weights, and that will be the functional group of alkenes. So if we look at alkenes, we can clearly see now on alkenes we have what? We only have hydrogens and carbons. So therefore an alkene is going to be a hydrocarbon because we only have hydrogen atoms and carbon atoms. But now, is this alkene saturated? No, alkene is not saturated because we have now triple bonds in between what? In between carbons. If we have more than one bonds in between carbons, therefore we're going to have what? An unsaturated molecule. That means now if we break these bonds here, we will be able to fill it up with other hydrogen atoms. So that is what makes now an alkene. So now if we move down here to talk about a haloalkane. So now if we look at this word here, haloalkane. So the halo part simply means halogens. And then we know that halogens are all the elements that we find in the periodic table, and they're situated in group number 7 of the periodic table. But now in these haloalkanes, we have now this group which is called alkanes. And remember now, alkanes is just the single bonds in between the carbons and other elements such as hydrogen. And now we have to include a halogen. So now we can have a simple example of a structure whereby we have 3 carbons that are now bonded to, let me just use a green color. 3 carbons bonded to hydrogens. And then now 1 carbon bonded to now what we call now a halogen. Okay, so now a halogen, it can be any element in group number what? In group number 7. For example, we can talk about a bromine. Okay, we can talk about fluorine, we can talk about chlorine. All those elements in group number 7, those are called halogens. So now if you look at this structure here, we are having single bonds, but now we start to have a halogen. That is why we say this homologous series is a haloalkane. Simply because we have alkanes, which is single bonds, but now we have a halogen included in that part. So now, if you remember, the equation of what? Of alkanes, it was CnH2n plus 2. But now do you see now, in place of 1 hydrogen, we have removed the hydrogen and then we have replaced it with a halogen. So that means now the general formula will now swap to change to be what? Cn, and we have 2n, but now we have plus 1 because we have removed 1 of the hydrogen and we have replaced it with a halogen. So now a halogen is all the elements in group number 7. So we write them as X because now it can be chlorine, it can be fluorine, it can be also bromine, like that. So now X will represent now the halogen. Okay, so now if we look at this structure that we have of a haloalkane, if we wanted to maybe describe the chemical structure of what we have, we were going to substitute now the number of carbons, which is 3 carbons, And then we're going to say now, to get the number of hydrogens, we're going to say 2 multiplied by 3, and that's going to give us 6. And then we have to add 1 hydrogen, and that's going to make what? That's going to make 7. And then now we're going to have to put now the type of halogen we have. And that halogen we have is a bromine. So we're going to put now a Br on that structure. So this will be the chemical structure of this formula. So now, do you see now for 3 carbons, we have 7 hydrogens and 1 brome. So you will, if you count now, you have 1, 2, 3, 4, 5, 6, 7 hydrogens, of which they are correct there. And then we have now 1 bromine. So that means the general formula will be given as that formula, okay? So now, what distinguish now the functional group? It will be this part here, which we call a halogen. Remember now, we had a functional group of a alkane having a carbon that is bonded to another carbon, and then bonded now to different types of hydrogen. But now, in this case, what will distinguish this functional group? It will be what we call now a halogen. So if ever we have a carbon bonded to a halogen, then that will make that to be a haloalkane. So now in this case, it doesn't matter if ever a carbon is bonded to a carbon can be bonded to a hydrogen or whatever way. But now, what distinguishes a haloalkane is if a carbon is bonded to a halogen. And therefore, that will be the functional group of what? Of a haloalkane. So now, if you will have to name or describe this type of a functional group, you will just call this a halogen atom bonded to a saturated atom. So you can just say halogen. You can just say this is a halogen atom. But we know that this halogen atom will be bonded to this saturated carbon. Remember now, saturated simply means it is having single bonds. So to describe this functional group, you will say now halogen bonded to a saturated carbon, if you will have to describe it in words. Okay, so now if we look at this part here, which you call a haloalkane, so on haloalkane, we don't have to necessarily, we won't be asked if ever is it saturated or unsaturated. But now, if you were to be asked now if this thing is saturated, yes, this thing will be saturated because now we only have single bonds. And then remember, saturated simply means we have single bonds in between the atoms. But now, is this thing now a hydrocarbon? No, it is not a hydrocarbon because now we have a halogen that is included. So this is not a hydrocarbon, but we can say this is what? This is saturated because we have what? We have single bonds. Okay, so now we're going to move on to the next type of a homologous series, and then this type is called alcohols. So now the way we see an alcohol, it is if we have carbons, and then now on any type of a carbon, we will have now what we call now hydroxide being bonded to it. So now OH is hydroxide. So now if we have a hydroxide bonded to a carbon, therefore we are going to have now what we call an alcohol. So an alcohol is represented by this OH that is bonded to a saturated carbon. So now, if we were to describe now the general formula of this particular thing, do you see now here in this case, we have replaced one hydrogen with OH. So now remember, if we replace one hydrogen, the general equation, it will just decrease to be Cn, then we have H2n plus 1. We have plus 1 because we have removed one hydrogen. So now you don't include this hydrogen on the part of the equation. So you just include this thing as hydroxide. So that means your general formula will be that, and then you have now OH, which is now the hydroxide. So if you had to write down the molecular formula of this particular compound, you will say now you have 3 carbons, and then you will substitute them in your formula. So you have C3, And then now, what will be the number of hydrogens? That means you're going to say now 2 multiplied by 3, which is 6, and then you add 1, and that is going to give you 7. And then now you just put now the OH. Remember, the OH, it comes after everything. So if you look at this, how many carbons do you have? You have 3 carbons. And then how many hydrogens do you have? You have 7 plus that 1 there, which means you have 8. And then if you count, you will say 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And then you only have now 1 oxygen. So do you see now this chemical formula? It is the same number of elements that we see on the structural formula. So now, if we look at this alcohol, an alcohol will also have its functional group. So remember, you need to know how to draw the functional group, and you also need to know how to name the functional group. So now the functional group of a carbon, it is described by this hydrogen oxide bonded to a saturated carbon. So that means you were going to draw it like this. You say now we have a carbon that is bonded to hydroxide, and therefore this carbon can be bonded to other carbons. It can also be bonded to hydrogens. It really doesn't matter. As long as we have now a carbon that is bonded to hydroxide, then we're going to have an alcohol. So now the type of name of this functional group, we're going to say now the name is hydroxyl. It's because now you see now we have oxygen and hydrogen that is bonded to what? To a saturated carbon. So we're going to name this what we call now a hydroxyl. So if they said you must name the type of the functional group, you will say hydroxyl. If they say you must draw the functional group, you will draw this functional group as it is. So now, if we get now to alcohols and other types of things, we will automatically see that this is not a hydrocarbon because now we have oxygen included. But now, if they ask you now, is this saturated or unsaturated? You will just say, okay, this one will be saturated because what? Because we have now single bonds. But now, saturated and unsaturated only applies to where we have carbons bonded to hydrogen atoms only. So now, if we move to this, the next homologous series, which is now an aldehyde. So we'll see now an aldehyde is actually a type of organic molecule whereby on the chain of atoms, the last or the first atom of carbon will be bonded to oxygen. So if this happens, we're going to say now this type of an element or this type of organic molecule, it will belong to what we call aldehydes. Because now aldehydes, they have what? On the first or on the last carbon, we have a double bond oxygen. So remember, it must be on the first or on the last. Okay? So now, if you look at this, what is happening is that the general formula, it is going to now be CnH2n. Because now, you see now on the carbon, we have removed 2 hydrogens and we have replaced them with what? With oxygen. So we're going to have what? CnH2n, and then we're going to put now the oxygen. So this will be the general formula for aldehydes. So now, if you look at the general formula of the aldehydes, if we wanted to find the chemical formula of the following, we will substitute now the number of carbons we have. So in this case, we have 4 carbons. So that means now the number of hydrogens will be 2 times 4, which is now going to be 8. And then we put now that oxygen. So now, if we count to check how many hydrogens we have 1, 2, 3, 4, 5, 6, 7, 8, which is correct. And then we have that 1 oxygen. So this chemical formula, it correlates with the number of atoms we have on that structural formula. So remember, when we talk about an aldehyde, it is whereby on the last carbon, we have what? We have a double bond oxygen. So now the functional group will just have that last carbon being bonded to what? To a oxygen, and then this carbon can be bonded to other carbons, but now it must also be bonded to a hydrogen. So now in this case, you must specify that the last one must be bonded with hydrogen, because it is going to be oxygen being bonded with a hydrogen to that carbon, and then the chain can continue as it goes with other carbons like that. Okay, so now the name of this functional group, we call it a family. So now if you talk about an aldehyde whereby you have oxygen, carbon, and hydrogen, that name of the group, we call it a family group. Okay, so you must be able to remember the names as well as the structure of the functional group. Okay, remember from there, we don't have to talk about saturated and hydrocarbons. So now we can just move on now to talk about ketones. So if you look at ketones, ketones are having a similar relationship to aldehydes. But now on the ketones, the double bond oxygen is not in the first or the last carbon. If ever the double bond oxygen is now in the carbon that is in between other carbons, then we're going to name that as a what? As a ketone, because a ketone is whereby we have a double bond of now this oxygen being bonded to carbon, but now it is not on the what? On the first bond. So now if it is on the second, on the third, but in between the bond, not on the first and on the last, then we say now that is a ketone. But remember now, if it is on the last, we say that is an aldehyde. Please don't let these things confuse you. And then you will see now, because now this thing here is just a position of the oxygen changing, we are going to have the same general formula, which is CnH2n. So for the same number of what? For the same number of carbons, we are going to have the same chemical formula. But now we have different functional groups. We have different homologous series just because the oxygen is bonded to a different carbon. Okay, so now that means obviously the number of carbons is going to be 4, and therefore the hydrogen is going to be 8, and then we have 1 oxygen. So if you were to count there, you will see now this thing will relate to that chemical formula. And then lastly, if we now draw out the functional group, you will say now, okay, the carbon, it must be a carbon in between other carbons. So you need to show that this is bonded to other carbons. And then these other carbons can be bonded to whatever they want to. But now this one here in the middle, it must strictly be bonded to oxygen so that we can have that functional group, which is now a ketone. So now once this oxygen is bonded to a carbon, and we're going to say now this oxygen is only bonded to a carbon. And then the name of this functional group is going to be a carbonyl. We're just going to name it carbonyl group. It's because now this oxygen is only bonded to a carbon. And then now this carbon will be bonded to other carbons. Remember in this case, on what? On the aldehyde, we had now the oxygen bonded to the carbon, but now it will always have to be bonded to a hydrogen. That is why we call that a family. Okay, so now we're also going to look at now the last two homologous series, which we have now carboxylic acid and esters. So now if we look at carboxylic acid, a carboxylic acid is also going to have the same relationship whereby on the last carbon, we have a double bond oxygen and we also have a hydroxide. So now this is happening on the last carbon. Okay, so now if this is the case, then we're going to have now this as what? As a carboxylic acid. So now a carboxylic acid, that means we have what? We have chain of carbons, but now on the last carbon, we have a double bond oxygen and we also have a hydroxide bond to that saturated that bonded carbon. Okay, remember now this carbon here is not saturated because we have double bonds. So now we're going to have the hydroxide being bonded to carbon that is bonded to that oxygen there. So now, if we were to describe now the general formula of this carboxylic acid, we will say now we have now the number of carbons, which is now 3 number of carbons. And then do you see now on this number of carbons, we have replaced what? We have replaced 3 hydrogens, because now this oxygen is taking 2 bonds of hydrogen, and then this one here, it is taking 1 bond of hydrogen. So this means now the general group is going to be what? Is going to be H2N, and then we have to minus 3 from the general equation of alkanes, which is plus 2, so that's going to be minus 1. And then after we minus 1, you will see now we have to add what? We have to add 2 oxygens that are bonded to hydrogen. So now that means the general formula will be oxygen and those 2 hydrogens there. And that will be the general formula of what? Of carboxylic acid. Okay, so now in this case, the general formula of carboxylic acid, you can write it as it is like this, because now remember you have 2 oxygen there. And this one is not 2 hydrogens, because now it is only 1 hydrogen here. I meant to say 2 oxygens, because you have those 2 oxygens and that 1 hydrogen at the end. So now this thing here, on this part of carboxylic acid, you can just represent this 1 of hydrogen as part of the hydrogens. So this means now this hydrogen will add to that 1 there, and therefore your general equation will just reduce to be CnH2nO2. Okay, so this only applies to when we have a carboxylic acid, whereby this last hydrogen can replace now that minus 1, and we have now CnH2nO2. And this will be what? This will be the general formula for a carboxylic acid. So now if we were to determine now the organic, if we were to determine the molecular formula of this compound, we will say now for 3 carbons, we're going to have 3, and then we have now 2 times N, which is going to be 6 in this case. We're going to have now 2 oxygen. So that means this will be the general or the molecular formula of this particular carboxylic acid. So now the functional group of what? Of a carboxylic acid, it is given as what? As whereby the last carbon is bonded to a double bond oxygen and also bonded to a hydroxide. And then the name of this functional group, it is called a carboxyl. It is called a carboxyl group. So now if you have now this carbon bonded to oxygen and then it is also bonded to hydroxide, we call that a carboxyl. And then that is the what? That is the name of the functional group of what we call now a carboxylic acid. So now if you look at esters, esters will have what? Will be the only type of what? Of an organic molecule whereby you are going to get an oxygen in between the carbons. So let's say, for example, we have the following. We have now the oxygen in between the carbons, and then now one of the carbon will be bonded with now a double bond oxygen. So now if that is the case, then we are going to have what we call now an ester. Okay, so an ester, it happens if ever we have an alcohol reacting with what we call a carboxylic acid, and then we will get an ester. But we will talk about that in the future. So remember now, this thing can continue with different elements like that. But now in this case, we're just gonna throw it as it is like this. We have 2 carbons, and then in between those 2 carbons, we have now this oxygen. So remember now, this oxygen in between the carbons is the one that describes an ester. So now the general formula of an ester will have the general formula that is the same as what? As the carboxylic acid, which is now what? CnH2nO2. And then if you were to determine now the number or the molecular formula of this particular thing, you will say now you have 2 carbons. So now for 2 carbons, that means you will have now how many hydrogens? You will have 2 times 2, which is 4 hydrogens, and then you will have 2 oxygens. So you will see now you will have 4 hydrogens and you will have 2 oxygens for 2 carbons. And then now this functional group of this last one is just going to be whereby you have an oxygen in between two carbons, and then one carbon must be bonded to an oxygen. And it can be bonded with other carbons or maybe bonded with the hydrogen, but now this will be the functional group, whereby we have an oxygen in between carbons and then a double bond oxygen in on top of that carbon that is next to the one that is having oxygen in between. So I'm going to stop here with this lesson. Thank you very much.